communications because you'd be leaving trails of breadcrumbs. In other words, the robots, the balls, would talk to each other and that way establish a large area network where they can communicate information to each other and then back to the lander. Okay, so you'd leave a few behind as you went out. That's what those little lines are. That's called radio waves, but a little bit iconic. Let's talk about some of the details of this thing. So, plastic actuators. And the basic principle of the plastic actuator, as I say, it works on the principle of peanut butter and jelly. How many people here have ever had a peanut butter and jelly sandwich? We're watching now. He's going to get another elbow. Okay, so what you have is a very elastic film in here. It's dielectric, meaning it doesn't transmit electricity. You then have compliant electrodes on either side of it. What is a compliant electrode? It's something like silver powder in a grease. So it's conductive but can expand. You then put a high voltage across those electrodes, and what it does, it squishes out the jelly as it collapses. They're attracted to each other. You put a plus voltage on one side, a negative voltage on the other side. They're attracted, and it squishes out and expands. So to give you an idea of what the basic principle is like, this is a rigid frame. In here is a plastic sheet, just a few microns thick, a few 10,000ths of an inch thick, or a few thousandths of an inch thick, painted on both sides with a silver grease, and this is about that big. And you put a voltage across it, and if the video plays, you'll see that it does expand. It costs a few pennies to make, very simple, and works well most of the time. But then what happens is you have to capture that expansion by a frame, because what happens is it expands. So what you see here is one of our diamond-shaped actuators. This is a diamond-shaped frame, which is all plastic with a plastic hinge here, and put a voltage across the two sides. This is black because it's carbon grease, which is less expensive than silicone grease. And that's a 75-gram weight. And if we do this properly, then what will happen is you'll see this actuator expand and lift itself. It weighs about 5 or 6 grams, and it's picking up 75 grams. So you got this little light, little inexpensive thing able to do meaningful work. It can expand itself to twice, about 200%, to its original length.
How many amps are you putting through that to make that?
You're putting almost no amps through it, zero current.
So you just, okay, because of dielectric.
Right.
So what type of voltage are you using?
You're using 3,000 to 5,000 volts, kV. High voltage, but no problem because the currents are so small. And so you get dynamic responses up to about 10 hertz. There's some tricks to make them reliable and make them work effectively. I always say people people do these kind of simple experiments and then expect to be able to do something with it. And I say it's sort of like Faraday's law. For those of you who remember Faraday's law, where you were a kid and they gave you a battery and a nail, and you wrapped the wire around the nail, and then you put the two ends to the battery, the two ends of the wire, and the nail moved. And you say, I discovered electromagnetic propulsion. I can now make a motor. And then there was 75 years of engineering to go from this battery with this wire, and to make what powers your washing machine, so to speak. A lot of engineering to go into practical actuators. But we're almost there. We're pretty much there now. So that's what it looks like. And you can make something hop with it. Let's see. This is our latest hopping device. It consists of a thin plastic shell, 110 millimeters in diameter. It pumps energy into these carbon fiber springs. So this is just carbon and fibers, materials, and that's the cone actuator. So that's the polymer material, both sides coated on both sides with carbon grease, and weighs about 18 grams. So 18 grams is about a half an ounce. including the shell. So it's pretty cool that you can make these things so light. You can multi-layer these actuators to get more force out of them. These have 5 newtons, which is about 1.25 pounds of force. Strain's about 50%. Everything is very, very light in this because you really want to go to Mars with very, very light weight because, as I say, everybody knows that, well, maybe you don't know, but when you launch things in space, you wind up with a rocket that weighs 100 tons, to launch a 100-kilogram payload. So every ounce you put on the payload, the rocket has to get bigger and bigger because you've got to lift it off Earth and through the atmosphere and send it out. So you want to make things really light. So this is a video of one of our prototypes recently. So it weighs less than an ounce, 26 grams, and it'll hop about 1 meter, and it says hop to 2, so part 2. Part 1 wasn't so interesting. So what it does is it's going to go, the actuator is going to collapse, and it's going to pump down this energy higher than normal speed. It's going to pump itself down, strain it, and then it's going to hop. So this is about 60 centimeters, about 6/10 of a meter. Actually hops a lot longer than that. And what we learned from this experiment is we need to get a longer stick. So that gives you a sense of this prototype stuff. Now, where does the power come from? Fuel cells. And why fuel cells? Because what happens is... What was that? Oh. If you plot energy versus power, you find out that you'd really like to get a lot of energy out of this stuff, right? And energy means how much power you can get for how long a period of time. We don't need a lot of power. We run this thing at a peak power of about 0.5 watt. Was our idea for the entire system is computers, electronics, and its propulsion, with an average power about 1/10 of a watt. Because we're in no rush to go anywhere. We have time up there. It's not like we're trying to build a dragster, but we want a lot of energy. And so we get a lot of energy. We're looking for about 77 watt-hours of energy. And fuel cells have a lot of energy for their weight compared to batteries, dry cells. So, a battery is way down here, right? Don't get good response from batteries. Don't even get them here. Yeah, the only thing that comes close is the combustion engine, but you really can't run a gasoline engine on Mars or on the Moon. There's no atmosphere. You'd pollute the environment with a lot of... Well, you talk to scientists, and they're really concerned about you throwing a lot of carbon around. You don't want to throw a lot of carbon out onto Mars if you're looking for life, because your sensors will say, I found life. It's carbon. Right? We're all carbon life forms. You heard that before. Sugars are when they're burnt, become carbons. We give off carbon dioxide. You don't want to put carbon. So you're really working. So that we chose PM kind of fuel cells, which operate a decent thing, and it operates on air and or oxygen and a little bit of water, and a little bit of hydrogen. Puts out a little bit of water vapor, which is so small can be absorbed back into the ball without releasing it to the atmosphere. This is what they look like. Okay, that's about less than 1 inch across. So they look like that. In fact, what happens is you put some oxygen into them, you put some hydrogen into them, and what they give you? A little bit of water vapor and electricity. So you can build a system that would power a thing where you have that should read O2, oxygen, an H2 tank, oxygen tank. You put them in. They give you a sense of the size. It's about the size of a postage stamp. And you can then put it through. You got to kick it up to high voltages, as the gentleman said, and that's the size of the electronics to take the 1.5 volts out of the fuel cell and make it into 5 kV that we require, 5,000 volts. So very low power. Hopping, the control systems are way nothing. A big part